In this last compulsory video for week 1, we're going to look at our first Python package, the matrix library Numpy. Please open notebook 1.4 and let's get started. So first things first, in order to use the Numpy matrix library you need to import it, and most commonly this is done by using the shorthand NP. Back in the second video when I talked about lists, I said they were similar to arrays, making the assumption that you were familiar with the concept of arrays from your use of MATLAB. However, let's talk more specifically about how arrays are defined and used in Python. So in Python, arrays are lists of constant type. So typically they're going to be integers or floats to support matrix operations, but string and Boolean arrays are also feasible. They can be unidimensional, representing vectors, two-dimensional, representing matrices, or higher dimensional, tensors. One way of creating a NumPy array is to pass it a list or a nested list for higher dimensions. So in this specific example, we use a list of lists to create a 2D array where the outer list contains 2 inner lists, each with 6 variables, so this returns a 2 by 6 dimensional matrix. Each type of NumPy matrix is a class, all inheriting from a single base class, and they all share certain attributes including shape, which gives you the row, column and higher dimensions, size, this is the total number of elements, ndim, that gives you how many dimensions it is, so 1 for vector, 2 for matrix and so on, and dtype will return the type of data in the array. Outside of initializing an array from a list, there are a number of generally more practical ways for initializing a list using the following methods. These support initialization of arrays of all zeros, where the default type here, and in all cases, is to create a float. We could instead create a matrix of integers, where here we've passed the argument dtype equals numpy integer 16. So this will ensure that we have an integer type for our matrix. We can also create an identity matrix, where of course this has just got ones on the diagonal, or create an empty matrix. So in this case the entries are uninitialized. So this ends up with them being very, very small but not quite 0. Please note that all of these matrices are being created with shape 3 by 3, where the shape is being passed as a single argument as a tuple. It's also possible to use NumPy to create number ranges, which you can then pass to a for loop statement. A range, which creates a list of incrementing numbers. So if you supply one value, it will create a list that runs from 0 to 1 minus that number, such that when you pass this to a for loop, it's going to loop over 5 iterations. If you give it 2 values, then it will iterate in a range from the first and up to but not including the second number. So in this case, the range 5 to 10 includes the numbers 5, 6, 7, 8 and 9. It's also possible to increment by more than 1. For example, the range 50 to 80 in steps of 5 gives 50, 55, 60, 65, 70, 75. The increment does not have to be an integer. On the other hand, linspace is different. This is because it takes a range and divides it up into a specified number of bins. For example, this call asks it to split the range from 0 to 2 into 9 steps, inclusive of both numbers in the range. Next, let's look at random number generators. So NumPy has a wide range of functions for generating arrays of random numbers, of which these are a few. So NumPy random creates a matrix of random numbers in the range from 0 and up to but not including 1. These numbers are uniformly distributed. NumPy random.randint creates random integers in a pre-specified range. So here the range is given from 5 to 20. This is a tuple defining the shape, also here. On the other hand, random.randn samples random floats in the standard normal distribution with mean 0 and variance 1. So all these functions are actually being asked to create 3x3 matrices, but note in this last case, these dimensions are given separately, whereas in the other two cases, the shape is given as a tuple. Next, let's discuss reading and writing to and from files. So it's possible to read from a text file or a CSV file using Numpy load text. By default, Numpy will assume that the files are delimitated with spaces. So if it's a CSV file or a file with comma-separated values, you're going to need to tell it to expect commas as delimiters, for example, as shown here in the save example. You can also cast the type during reading using dtype, or format the precision of the output using this argument. Note that if you want more details on the options for string formatting, you can look at this link. On the other hand, Numpy has its own file format indicated by .npy files. These store all the information required to reconstruct an array, including the data type and shape information. It'll also read pickled files, where file pickling is explained in the optional video on file reading and writing. Slicing and indexing behave as for lists and strings. Indexing is from 0, range is not inclusive of the last index in the range. This also applies to multi-dimensional arrays. So in this example, we slice the first 2 rows indicated by the range :2 and all the columns from the second one onwards. The second example shows 3 ways of extracting a single row from a matrix. In the first case, we just ignore the columns entirely and ask for the second index. This is the same as what we would do if we were indexing a nested list. The second example specifies that you want the row corresponding to the second index, which is the third row, and it also asks for you to return the values from all columns. In the third example, it's asking for all rows from the second index to the end and all columns, which, because the second index corresponds to the final row, returns the exact same array as these previous 2 examples. And then this third example shows that you can return an arbitrary mixture of rows and columns by using lists to index the rows in this particular case. So it asks for the first row and the third row. So moving on, what we're showing here is how it's possible to return all indices or values from an array which meet certain conditions. So in this example, we are performing the Boolean operation, my matrix is greater than or equal to 4. Now, given this matrix, what this returns is a Boolean array of the same shape as the matrix, where the entries are either true or false depending on the condition. More commonly, what you'll use this for, though, is to actually return the values from the array that meet that condition. And in order to do that, you need to pass that Boolean condition in order to slice your matrix. In that case, it then just returns a list of all of the values from this matrix that meet this condition. So now let's look at options for changing the shape of arrays. The first thing that you might want to do is to stretch out some matrix, for example this matrix A, into one long vector. There are 2 different functions for doing this. One is called flatten and the other is ravel. They take argument order. This controls how the array is unraveled, such that C means to flatten the array in the same way as would be performed using C or C++ in row major ordering, such that when you unravel the array, it goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. On the other hand, you have the choice of taking a Fortran-like approach where it instead goes in column order, so 1, 4, 7, 10, 2, 5, 8, 11, 3, 6, 9, 12. So both of these functions perform the same operation of unraveling. The key difference between them is that flatten makes a copy, whereas ravel does not. Such that if you run a.ravel, then the object A will subsequently become flattened. On the other hand, if you run a.flatten, you're going to have to save it to a new variable, and that variable will be flattened, but A will continue to have the same shape. Now, the copying behavior of Python can occasionally throw up problems, and for more information on this, it might be worth looking at section 2.8.2 of the control flow notebook. So alternatively, you might not want to unravel your matrix. You might just want to change it to some arbitrary new shape as long as the total number of elements is compatible. So this can be done with reshape or resize, where again, reshape is going to create a copy and resize is going to modify the original array. Finally, it's possible to combine arrays with compatible dimensions using concatenate. So the syntax for this is to pass all the arrays that you want to concatenate within a single tuple and define what axis you want to perform the concatenation on. Clearly, this axis has to have the same number of dimensions for all arrays that you're concatenating, otherwise the operation is not going to work. For broadcasting, on the other hand, you are able to perform operations on arrays which initially at least have apparently incompatible dimensions, provided that the dimensions are either exactly the same or 1. This is because what Python is going to do under the bonnet is assume you're going to want a copy of the array along the dimension in which it is originally 1, such that the dimensions then become completely compatible. So for example, I can add this 3x4 array to this 1x4 array because the Python IDE is going to copy this 1x4 array 3 times until it becomes a 3x4 array. And then you can just perform element-wise addition, which is what's required from this plus sign operator. So talking about element-wise operations, Numpy offers a wide range of different operations, including add, which we've just seen with the plus sign, subtract, Numpy subtract, or just use the minus sign, element-wise multiplication using the asterisk or Numpy multiply, and element-wise division using the backslash or Numpy divide. When it comes to matrix product operations, it's worthwhile being aware of some diverging functionality of the following functions. So we have 3 functions here, numpy inner, numpy dot, and numpy mul, which for one-dimensional vectors will all calculate the dot product. So element-wise multiplication with summation. However, their functionality starts to diverge when you get to 2D arrays or matrices. So in this case, the inner product estimates the sum product, which is performing element-wise multiplication and sum of the rows of each matrix. On the other hand, the dot and map-mul functions will estimate the matrix product for 2D arrays. So that's multiplying the rows of A with the columns of B. Subsequently, at higher dimensions, there's further divergence between the dot product and the map-mul function. But to save confusion, the point that I'm trying to make is that for the vector dot product or matrix product, you're best using map-mul. Other useful matrix and vector products include the outer product, the cross product, and of course the matrix transpose, which you'll use a lot. Numpy also offers a broad range of different linear algebra operations. The most important ones for you will be eigenvector decomposition, matrix factorization. This is singular value decomposition. Numpy also allows estimation of the mean, the variance, the standard deviation. You can either do this for individual axes to estimate, for example, the means or variances of each row or column, but the default operation is just to estimate the mean or variance over all elements in the array. And Numpy also provides a number of other functions to perform element-wise operations, for example, to return the absolute values of a matrix or array, return the logarithms. For all the possible routines available in Numpy, you can take a look through the online documentation. So this wraps up this brief introduction to Numpy. To be honest, the best way to gain familiarity with Numpy and the matrix operations will be to use them. And so this will come naturally over the next few weeks as we work through the course. The key things to remember as you go forward are that in order to use it, you must import it, and the common syntax is to use the MP prefix. We discussed indexing and slicing in the context of lists and strings, and it's exactly the same here for arrays. When performing matrix flattening and reshaping, be conscious of whether you want to change the original matrix or create a new one. And remember that Python allows operations on two matrices without them originally having the exact same dimensionality, so long as it's possible to make the second matrix compatible through copying rows or columns. This is known as broadcasting. So this is the end of the video on Numpy. Please go through the Keats quiz to check your understanding of what we've talked about in this session. We'll practice it all in more detail in Tuesday's synchronous session.